A unified mathematical framework cannot simply assert the existence of complex topologies or dynamic fields. Before scaling up to network architectures or systemic loops, the modeling substrate requires a strict foundational contract. Chapter 0 of the Unified Harmonic Systems Architecture provides this contract. It fixes the base assumptions, uniform symbols, and admissibility rules required to ensure that downstream equations remain comparable across different scales. This begins with three primitives: continuum, core, and field. In this framework, these terms represent mathematically bounded states, governed by exact rules of topological persistence and spatial constraint. Locking these definitions at the start ensures that, as the model scales, macro-level field claims remain traceable to the same micro-level stability axioms. Classical modeling often treats the continuum as an empty Cartesian grid, a passive spatial void waiting for local objects to appear. UHS discards this view. The UHS continuum is an always-present, actively fluctuating overlap background. Any localized structure is a scale-conditioned presentation of this same substrate. What is traditionally called a medium is the local patterned organization of this background, rather than a secondary substance layered on top of a separate void. Stillness also requires a precise definition within this overlap background. Structural rest is not a claim of absolute inactivity. A configuration counts as at rest only when its remaining motion is shared with the chosen frame of reference. Treating the continuum as an active background allows localized core properties and broad field interactions to be evaluated through the same continuous modeling substrate. To track these structures, we represent the system state using psi as the configuration field, situated within the Sobolev space H1. The configuration space consists only of admissible psi instances, states obeying the framework's inherited topological constraints. Take this one-dimensional substrate. On the left is a smooth local ripple. On the right is a sudden vertical tear in the spatial data. The discontinuity violates the boundedness required for persistence and is out of model. The smooth perturbation is accepted as an admissible configuration. Because admissibility is based on these field properties, two physical arrangements with entirely different coordinate choices can map to the same admissible psi class. Defining the sandbox through admissible psi instances creates an objective mathematical space for checking invariance and comparing trajectories. Once a state is admitted, we evaluate its persistence using h of psi, the organizing stability functional. This functional provides the primary scalar measure comparing the persistence of admissible arrangements. The gradient term calculates spatial variance, measuring how sharply the field changes. The nonlinear self-trapping potential determines how the configuration anchors into a localized structure. Lower evaluations of H correspond to configurations the model treats as more stable. These stability comparisons are only meaningful when normalization parameters are held fixed across different modules to prevent hidden scale mismatches. Under this regime, any geometric arrangement yielding a lower functional value becomes the preferred resting state under bounded disturbance. To model how these states change over time, we define an admissible dynamics envelope. This separates valid transitions from structural breaks. We evaluate perturbations by checking stability changes against an escape energy barrier. If total variance remains within the basin of attraction, the transition is valid. If a perturbation violently exceeds this limit, the configuration is forced out entirely. Disturbances that exceed the envelope degrade into the ambient background noise through assimilation, rather than disappearing from the model entirely. This test ensures that all reaction and transfer claims made in later modules remain anchored to a single verifiable inequality. We must now shift the analytical focus from the stable interior of the continuum towards its local boundaries. This landscape shows a state resting deep within a central potential basin, appearing perfectly stable. However, unconstrained interior analysis can create false positives. A configuration that appears persistent in isolation may fail when evaluated against its environment. We must examine the domain's extreme edges. This introduces the boundary consistency equation, centered on the surface's normal vector. States stable in the interior can fail at the edge. As variance spikes past the threshold, it forces a mathematical rejection. Boundary-sensitive regions stabilize differently than interior regions, even when subjected to the same perturbation magnitude. These interface assumptions act as a hard filter, determining which coupling claims are admissible. By separating these boundary relations from interior stability, we force explicit geometric checks before moving into localized bridge mechanics. To maintain the integrity of these checks, the framework locks its primitive vocabulary to prevent term drift. Substituting loose metaphors for technical terms like core or field breaks the mathematical dependency chains built into the modules. This creates a simple handoff rule. Any future claim must be traceable to the constraints established in this foundational chapter. These constraints are now passed to two distinct modeling targets: the highly localized stable core and the extended spatial wave of the field. Maintaining these mathematical boundaries at the substrate level protects the predictive power of the entire unified harmonic system. Module I will now use these localized stability requirements to define core dynamics. Module II will apply the continuum mode assumptions to define extended fields. With the admissibility sandbox built and the rules set, the theoretical architecture is ready to support multi-scale harmonic structures.